What is up, team? Here we are. Going to do a quick video for you today. You probably expected it to be not me, but guess what? It is. So we're gonna be basically just looking at some structures, some Lewis structures of polyatomic ions. This was very similar to the bonus, or the style is very similar to the bonus problem on your last quiz, right? Your quiz from Friday. Now, this is very similar to how we originally, or how we normally do Lewis structures. Now, with polyatomic ions, what does that mean? It means we have gained or lost electrons. So we have to break it down. So I have three main steps that just kind of break it down, make it simpler for you guys to follow along. And those three steps, as you can see, are how many electrons, AKA figure out how many electrons we're dealing with that ultimately need to be in your structure. That's the first step. Second step is find the central atom, figure out what's going to be your central atom, and then assign single bonds to each of those subsequent atoms. Because right now, those polyatomic ions are very simple. They have those central atoms bonded to bonded to the individual outer atoms. And then your third step is complete your octet for each one of those atoms, if possible. Of course, hydrogen doesn't complete an octet, but make sure you complete the octet and fulfill charges. What do I mean by that? You're gonna see what I mean here in a sec. Because sometimes these ions will have an overall charge that you need to fulfill, but you also need to make sure you fulfill the charge of each individual atom. We're gonna look at those here. So this will be on your test. So please make sure you know how to do this. So here's some examples. Let's look at nitrate, right? Nitrate is an atom, and the first thing, right? What was the first step here is count your electrons. Figure out how many electrons we're dealing with here. How do we do that? We look at the valence number for each atom. So we have one atom of nitrogen, so we know we're gonna have 5 electrons because of that one atom of nitrogen, because it's 5 valence electrons. And then 3 atoms of oxygen. We know that plus 3 times 6. We know that oxygen has 6 valence electrons, so 3 times 6 because there's 3 of them. And then finally, what do we see here? We see a negative sign that suggests an extra electron is in this structure. So plus 1 electron. You add these up together, that's 5 plus 18 plus 1, that equals 24 electrons. So we have our number. We know we want 24 electrons ultimately in this molecule. So what's our central atom? Most commonly, your central atom is the atom that is the individual, right? Oftentimes, you have compounds of like this that have 3 oxygens, 1 nitrogen. Therefore, nitrogen is your central atom. Okay, I'm going to switch over to this pen. Nitrogen is your central atom. What did step 2 tell us? Once we found the central atom, we assign bonds to each of the subsequent atoms. So we know we have 3 atoms that will bond to this, 3 oxygens. It doesn't matter if I put which order I put them or however I put them, but we know there's going to be at least a single bond, right? So that's what I mean by assign bonds, because we know there will be at least single bonds because they have to have something. And then the third step, right? Complete your octet and fulfill charges. So we need to complete the octet for each of these atoms and fulfill their charges. When I say fulfill their charges, I mean this overall molecule has a negative charge. So somewhere there's going to be an atom here, maybe multiple, which you'll see. There will be an atom here that will have more electrons than it naturally desires. But that makes sense, right? Because we're trying to achieve an octet. And if we're trying to achieve an octet, that means we have to gain extra electrons. So that's going to go somewhere here. You're going to see what I'm talking about. So our third step is to fulfill those charges and octet. The first rule I'd say is octet. And one of your most immediate thoughts here is, oh, to fill the octet of nitrogen, let's add a lone pair. But you'll see if you go over, and basically the way to find the answer at this point is a lot of trial and error. You're figuring out how to manipulate and where to put those electrons. But you'll see that if we did that, that would mean all the other electrons would be lone pairs. There would be no double bonds at that point, because if you did have a double bond, it would overload nitrogen if it also had a lone pair. So if we do it this way, then we've accounted for 2, 4, 6. Let me show you how I'm doing this. I'm counting 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Can we have 26 electrons? No, we cannot. So what does that suggest? That means that these are probably going to arrange a little bit differently. There's probably not going to be a lone pair, and there's actually going to be what's called a coordinate covalent bond, but you don't need to know that. Basically, what we end up going to do is one of those lone pairs of electrons is now going to be a double bond to that nitrogen. Does it matter which one? No. That's what's called resonance. And we're gonna talk about that more later, but let's just say it's those electrons that form a double bond. So what happens is they say, okay, we form a double bond here. Now let's assess our octets for everyone, right? And let's assess our number of electrons. We have, let's count our electrons first. Actually, we're not gonna count our electrons. You just saw, we know we have 24 electrons at this point, right? You can count them up and you can see we have 24 electrons here. So that's our first step, that's our desirable. Now, does everything follow the octet? Does everything have 8 electrons that are bonding with it or are a lone pair on it? Let's see. We've got 2, 4, 6, 8 for that oxygen. Great. 1, 2, 3, 4 bonds on nitrogen, which means each bond has 2 electrons. So we have 8 on nitrogen, 8 here and 8 here because you get 2, 4, 6, 8 right there. So you do see that we have full octets everywhere. Now we have to assign or fulfill charge. What do I mean by that? Let's take a step back. What is the number of electrons nitrogen, let's say, what is the number of electrons nitrogen normally has? It has 5, right? And so there's a rule for charge of these that bonds mean, obviously there's 2 electrons bonding between, but we're suggesting one of those electrons is nitrogen's, one of them is oxygen. So when you look at bonds, for the sake of charge, bonds only count as 1 electron. So if you look at how many electrons are directly on this nitrogen, you get 1, 2, 3, 4, but we know nitrogen has a valence of 5, so that suggests that there's the presence of a formal charge. Whoop, if my thing will work. Okay, and now will it work? Yes, there's a formal charge, aka a positive charge there, because you have 1 less electron than you naturally do in nitrogen valence. So you have a positive there. And we have to check and see what happens to everything else, because oxygen has its perfect 6, right? Because it has 2, 4, 6, 8 there, right? I didn't do that right. I meant 1, 2, 4, 6. Why did I go 1, 2, not 2, 4? Is because remember, for the sake of charge, electrons in a bond, you only count 1 of them when we're talking charge. So that means that oxygen has no charge here, but you look at these oxygens and they each have 7 because 1, 3, 5, 7, right? So there's each 7 there, which means they have 1 more than they normally do in their valence shell, which is normally 6. So we have an extra negative charge there, negative charge there. And so let's look at those formal charges. Positive 1 and negative 1 cancel each other out, and you have a negative left over. That goes directly with what we needed in the start. So this is a proper Lewis structure here because you need 1 negative charge overall for your molecule. That's suggested there, right? Maybe you got this, maybe you're not quite there. Let's do more examples. And I really mean this when I say the third step is a lot of trial and error. Put things on there, assess it, and if it's wrong, start over. It's like a puzzle, right? It's not always you're gonna get it the first time. So let's look at number 2, carbonate, right? We have CO2 negative, or CO3, 2 negative, right? So first step, count those electrons. What do we have? We have 4 from carbon. We have 3 times 6 from oxygen. So what's 4 plus 18? That's 22 plus another 2 electrons. Looks like we have another 24 electron atom or molecule here. If you're curious where I got that, 4 from carbon because it's in the 4th group, 6 from oxygen times 3 is 18 because there's 3 of them. Oxygen's in the 6th group, 2 extra electrons. Great, cool. Wow, didn't mean to do that. Okay, anyway, let's start with our central atom here, carbon, of course. Bonded, we put individual. It's looking similar to our last one, okay? So we have individual bonds here to each of these carbonates. We know that we're gonna need 2 negatives, right? First step here is fulfill the octet of this atom, or of this central atom, right? And we know that there's 2 options here. One of these can become a double bond, or carbon can have a lone pair. Now, if carbon has a lone pair, that will give it a negative charge, which doesn't necessarily mean it's a bad thing because we do need 2 negatives here, but let's try to avoid first putting a charge on our central atom if possible, especially because oxygens normally take charges really well because a single bonded oxygen naturally gives a 1 negative charge. So instead of putting a lone pair here, let's experiment and start kind of like we did last time, and put a double bond to one of these oxygens. Now that we've put a double bond there, we've fulfilled carbon's octet of 2, 4, 6, 8 electrons around it. So we can start filling in those lone pair electrons. And I'm filling in based off of the number of electrons I'm given, right? Because right now in this bond, there's only 2, need to do red. Right now in this bond, there's only 2, 4, 6, 8 electrons, and we need a total of 24. So we start piling on those lone pairs. So we get 2, 4, 6, 8, 10. I'm sorry, I'm not saying that right. 2, 4, 6 plus our already present 8. So there's 14 in total now, right? 16, 18, 20 in total now. 22, 24, hold the phone. We've applied all of our electrons. Let's see how we're doing, right? Well, it looks like this has a complete no charge neutral octet filled because you have 2, 4, 6, 8 filling oxygens octet, but you have 1, 2, 4, 6 for its charge, which is what it desires. So there's no charge on oxygen. Carbon's the same because it has 4 valence electrons and it has 4 in relation to it. So no charge there. Now we do see a negative charge on this oxygen because it has 7 electrons around it when it only when it only normally has 6. And then oxygen over here, same idea. So that's actually a perfectly drawn Lewis structure because we had 2 negative in our overall molecular formula. So if it matches, it matches. Heck yeah, good job. Now I'm going to stop here. I know that some of you have this question. Well, what if that electron or that double bond was here and then this was like that one? That's totally fine. And that's an idea called resonance. And we're going to talk about that in your video tomorrow. So let's do one more example. I'm going to fly through this one. If you need help on these, please reach out. I want to make sure we set up a time to go over these so you feel confident before your test on Friday. But let's do one last one here. Central atom, of course, is phosphorus. Oops, skipped my first step. Let's count our electrons. Phosphorus is in group 5. Oxygen is in group 6. So 6 times 4 is 24, plus 5 is 29, plus 3 extra electrons suggests 32 total electrons. Check my math there, but I'm pretty sure I'm right. All right, so let's break it down. We know we have 32 electrons needed here. We have phosphorus as our central atom. We know that oxygen is going to be the 4 electrons around it. And I want to tell you now, there are 3 atoms that you will see that with our class that are exceptions to the octet rule, that can exceed the octet rule. Those are sulfur, phosphorus, and xenon, right? There's actually other noble gases that can, but for the most part, sulfur and phosphorus are the only 2 that we really focus on. And so know that those can exceed the octet rule. They can have more than 8 around them. So that's going to be important for this problem here. So what we see now is we have phosphorus here, which with a 3 negative charge, 32 total electrons. And so my first thought is, oh, phosphorus has a completed octet. It desires 5 electrons. And if it only has 4, that would be a positive charge. We could totally have a structure possible if we just left that there and then add in lone pairs, because that would mean each one of these oxygens would have a negative charge. And so let's count up how many electrons that would be, shall we? Because at this rate, we have 4 negative charges and 1 positive charge. And when you add those together, you get 3 negative charges desired. But let's check and see if that works. So we'll break it down. We have, I'm going to go to my red pen. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Yes, that does totally work. And if you put this on a test, that would be a possible answer. But I'm here to show you there's also another possible answer, another resonance structure that, again, wouldn't technically be wrong. And it would actually reduce our number of formal charges, because at this rate, you'd have 4 formal charges, right? You'd have each one of those with a negative charge. So I'm going to do a whole bunch of undoing and show you that there's another way you could have done this, right? So that answer would be totally correct, or this answer would also be correct, assuming we follow that octet rule. Okay, so let's figure it out here. So if we assigned a double bond, since we know phosphorus can exceed the octet, that would allow phosphorus to meet its desired 5 electrons, because phosphorus normally has 5 valence electrons. And so you'd then have a double bond, and that would suggest, okay, let's apply lone pairs like normally we would, and we go here. All right, so we're breaking down, we're applying all those. Yes, 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 yes. Great. We have 3 formal negative charges because we know that when oxygen has 7 electrons around it, that's 1 more than 6. So that's where that negative charge comes from. Phosphorus has no charge because it desires, or not desires 5, everything desires 8. But phosphorus normally has 5, and it has 5 coming from each of those individual bonds. And then you have 1, 2, 3, 4, 5, 6 around this oxygen here. So that also doesn't have a charge. So this would have also been an acceptable form of this Lewis structure. And that's demonstrating the idea of resonance, the idea that there's multiple ways that structures can be for certain atoms. Now, they have predominant or most abundant structures, but it's cool and important to recognize there's multiple different resonance structures. And depending on what resonance structure reacts with a different atom or molecule, it will create a different product. So that's just a little bit of our lesson today, going over more complex Lewis structures like polyatomic ions. I know these can be confusing, so if you want extra practice, reach out to me. We can set up a time, whether it's tomorrow, being Wednesday if you are watching this on Tuesday, or Wednesday if you're watching this on Monday, and then we can make sure you're feeling good and ready for your test on Friday. That's all that I have for you guys today. Sorry if this was a little long. I have no idea how long this has taken, but thank you guys for sticking around. Have a great